Hi, in this video I will talk about a few model performance measures available in Design Expert to check the performance or the goodness of fit of the regression model that you create. I will also comment on a few specific plots for checking model residuals and influential points, and thereby checking the model assumption, those plots that are available in your software. Also remember that you have the topic help function in your software where you can check some more details about the plots and formulas and things that happen behind the scenes of the plots that you see. So I will not go into all the details in this video, so some of them you can check by yourself in the software. Okay, so in order for us to have something to look at in this video, I will work with this example 6.1 from the course book in the software. So this is a two-level factorial design in 3 factors. It's replicated in 16 runs. So it's a 2 to the 3 design with 2 replicates. And the response is the edge rate, and then you have 3 design factors. Factor A, which is a gap between some electrodes, factor B, which is a gas flow, and factor C, which is a power of some sort at the cathode. All right, so let's quickly move into the half normal plot with some green triangles appearing in the plot. So I was thinking that this is something that you should take notice of, and maybe there's a need to explain what this is actually doing. So you can see those green triangles here, and in the plot it says error estimates. So basically what we have 8 degrees of freedom from the replicates for the pure error estimate. So the software will simulate 8 effects with expected value 0, väntevärde 0, but with the effect standard deviation based on the pure error estimate available from the replicated runs. So we know that these 3 green triangles, or the estimated or simulated effects, have expected value 0. And their variation around 0 is only based on the pure error estimate. So these 3 triangles, they can be a good way to find the slope of this red line that you see here in the normal plot, and that way try to pick out the active or significant model terms or effects from the plot. However, when you have replicates, we usually go directly into the ANOVA table because we have the pure error estimate in the ANOVA table, as in this case. So here you have the full ANOVA model, or the full model in the ANOVA table. So you have the 3 main effects, you have 3 two-level or two-way interaction effects, and one 3-factor interaction also. And here you also have the pure error estimate. We have with the 8 degrees of freedom and the mean square for pure error here. And this way we can do the test without subjectivity, let's say. So we can look at the p-values with which are quite independent on the analysis, or independent on which factors we believe to be significant and so on. So these 3 factors, it's the main effect of A, C, and the AC interaction. They have very low p-values, so it's a reasonable conclusion to believe that these 3 factors should be in the final model. So let's reduce the model and just keep those significant terms and look at the ANOVA this time. Now we have only the significant variables or significant effects or terms in the model. We can also see that we get this lack of fit sum of squares, which is the sum of all the sum of squares for the eliminated effects from the model. You still have the pure error estimate the same from the 8 degrees of freedom you get from the replicated runs. We can also see that the lack of fit is not significant, which is good. So we don't seem to have any lack of fit in the model, which is a good thing. Okay, so now let's move on to the regression model fit statistics, which you also get from the software. So it will provide you with some fit statistics or performance measures that you should evaluate. Perhaps the most important ones are these three: the R squared, the adjusted R squared, and the predicted R squared. But anyway, let's go through those that you have. You have the standard deviation, which is basically the square root of the mean square for error. You have the mean response in all experimental runs, and then you have I think it's called the coefficient of variation, which is this measure. You have the standard deviation divided by the mean times 100. So it's like a percentage of some sort. Doesn't mean too much, so I shouldn't recommend that you take much notice of that actually. And then you have the R squared. You have the formulas for the R squared, the adjusted R squared, and the predicted R squared over here. And you see that the predicted R square, to calculate that you need the PRESS, which is the prediction error sum of squares, which is sort of calculated by removing one observation at a time, re-estimating the model, predicting that observation, and checking the let's say the sum of square or the deviation from the predicted observation and the real one. You put that back, you take the next observation out, and you do the same for the observation 2, put that back, take number 3 out, and so on. And summing those squares of those deviations become the PRESS statistic, which you need to calculate the predicted R squared. The software will also give you some, let's say, help text. For example, it will try to check if there is more than 20% or 0.2 units difference between the adjusted R squared and the predicted R squared, and if it's more than 20% or 0.2 difference between those, it might be an indication of some problem in your model. The adequate precision is basically a signal to noise ratio. The software states that it's nice to have a signal to noise ratio above 4, and this ratio in this example is 22, so it's indicating an adequate signal. So the model can be used to navigate the design space in a good way. Okay, so those regression model fit statistics are very important to have some idea about how good the model fits the data, and also to have some idea about the predictive ability of the model as well. Okay, you also get estimated model coefficients. In this case, we're looking at the coefficients in terms of the coded factors. So you should notice that the coefficient estimates will be different if you work in coded factors, that is -1, +1, or in the actual or real variables. You will also easily get the corresponding regression model from the software. So this is the regression model you get for the edge rate based on the coded variables. And notice that the regression models that you see are based on only those effects that you keep in your model that you find significant, for example. And here you have the corresponding estimated model for or in true or real variables, if you would like that one as well. Okay. So I will now move on to discuss some part of the or quickly discuss the residual plots and plots for influential points that you have in the software. So you have 5 basic residual plots, and they will try to help you to determine if this assumption of normally and independently distributed residuals with mean zero and constant variance, if that assumption is reasonable or not. You also have one plot to check the potential need for a transformation of the response. And you have 4 plots to help you check for influential points or influential experimental runs that have had a lot of influence on the, let's say, the model that you have created and so on. And these points, influential points, if you have those, you might want to go back and check that the recorded data you have for those influential points are actually accurate, or if there was some recording error or something like that in these runs. First, we should also be aware that this setting of externally studentized residuals is the default setting in Design Expert, as far as I know. This can be changed to looking at the ordinary residual or the internally studentized residual in the software. So without going into the formulas that you see, so the externally studentized residual is sometimes called outlier T or R student. This is calculated by leaving each run one at a time out of the analysis and estimating the response from the remaining runs. So it's somehow similar to how we do with the press value. But anyway, the T value that is given in the formula is the number of standard deviations difference between this predicted value and the actual response. So the externally studentized residuals that test whether the run in question follows the model with coefficients estimated from the rest of the runs, whether this run is consistent with the rest of the data for the model, and so on. And runs with large t values should be investigated. This is a text from the help, topic help in Design Expert. So, but you can easily go, if you would like to look at the real residuals, the prediction errors, if you would like that. But it's recommended that you use those externally studentized residuals, and by doing that, you will also get some, you can say almost like control limits or and the like in some of the plots. You will get red lines that help you locate strange deviations in some residuals and so on. If you look at the standard or ordinary residuals, you will not get those red lines that help you in the residual analysis. So it's a good recommendation. It's good to try to understand what these externally studentized residuals actually are. Okay, so let's look at the 5 basic residual plots for this example 6.1 based on those, keeping only those 3 effects AC and the AC interaction in the model. So we have the normal plot of the residuals to check the normal distribution assumption. We have residuals versus predicted value to check if there's a connection between the predicted value and the prediction error or residual. Sometimes we're looking to see if there is some sort of funnel shape like this, which is quite common, that with higher predicted values you would get an increased variance in the residuals. Doesn't seem to be that in this case. Then you have residuals versus run order to check if the model's predictive performance changes over time as the experiment was performed, which might be an indication of something strange happening during your experiment. And you also have residuals versus factor level to check if the residuals are independent of the factor level settings in the model. And you also have this predicted versus actual. So this is a graph of the predicted response versus the actual response values. And the purpose of that plot is to try to detect a value or a group of observations, let's say, that are not easily predicted by the model. So these are the 5 basic plots that are important to look at. Next, it says 2 plots to check the need for transformation. Should say 1 plot to check the need for a transformation. The box-Cox plot for power transformations. So this plot is to try to help you select a proper power transformation. So trying to transform your response values by taking y to the power of lambda. So it checks for the optimal value of lambda, and the optimal value is where this natural logarithm of the residual sum of squares is minimized. So the optimal lambda in this case was 0.8, but this this plot will also give you a confidence interval, which is from minus 1.88 to 3.85. And if this confidence interval includes 1 here, which means that lambda is equal to 1, no transformation, then there will be no recommended transformation. So this is what you see here. Recommended transformation, none, lambda is equal to 1. But this is a helpful plot to try to see if there might be a need for a transformation. Okay, so here you have 4 plots to check for influential points. You should check the topic help function in the software for a more detailed explanation. And you also get some formulas if you'd like that to see what's actually going on. So I will go through these plots quite fast and try to explain what you're seeing in the different plots. First, if you look at the Cook's distance plot, this is the Cook's distance is a measure of how much the regression would change if the observation was omitted or eliminated from the analysis. So if you have relatively large values of the Cook's distance, these are normally associated with high leverage values and large studentized residuals. And if you have large Cook's distance values, you should investigate those response observations, to see that you do not have any recording errors or something like that that affects the model in some strange way. Then you have the leverage of the design points. This is something that is based only on the design itself. So the leverage of a point will vary from 0 to 1, and it will indicate how much an individual design point will influence the model's predicted values. A leverage of 1 indicates and means that the predicted value is forced through that observed value. So the model will be forced, or the predicted value will be exactly the same as the recorded or observed value in the experiment. So in some sense, leverage values of 1 is not desired. The leverages are determined by the diagonal elements of the hat matrix, which we talked about earlier in a previous video. Then you have 2 plots called DF fits and DF betas. We start with the DF fits, which is some sort of measure on the influence that the ith observation has on the predicted value. It is the studentized difference between the predicted value with observation I in it and the predicted value without observation I. So it's a way of looking at influential points for the fitted model. And then you have DF betas. This statistic is calculated for each coefficient at each run. You can change the which beta coefficient that is checked in this plot. So in this case, we're looking at DF betas for A or beta for A, but you can also look for beta 0, for example, and so on. And this plot shows the influence that the ith observation has on each regression coefficient. So these two plots together can be used to find influential points for the fitted models and the fitted parameters of the model. Okay, with that, I thank you so much for listening and good luck with the software. Thank you.